Boom! Alright, so welcome to yet another one of our videos where we delve into topics on the CSEC mathematics syllabus. Of course, if you come in here to deal with mathematics from some other place, that's not a problem. Welcome, maths is maths. Alright, so in this video we're going to start the conversation on vectors. Alright, and as I like to do as often as I can, I'm going to take some time now to just talk around the topic, delve into some of the concepts, delve into some of the ideas, try to give some examples that hopefully you'll be able to relate to. And then after we do that, we will get into the mathematics of it. All right, we try to understand the topic first and then deal with the maths, the computation and the figures and all of that. So we're talking about vectors. Now, when we talk about vectors, we immediately, by implication, which is to say, whether you realize it or not, you're actually making a very direct contrast between vectors and scalars, what we call scalars. All right? We have this thing where we refer to as a vector quantity, and we have this thing that we refer to as a scalar quantity. All right? Students of physics might be a little more familiar with the terms, but even if you're not a student of physics, that is all right. Cool? So I'm going to give some examples of scalars, and then I'm going to give some examples of vectors, and then we will start to differentiate between the two. So some examples of scalars that I picked up on the internet are things like mass, speed, distance, time, area, volume, density, temperature. I would like to also include things like weight, right? That's a scalar, right? If we're talking mass, we could say weight as well. Mass and weight are not the same, but they kind of closely related to each other. And weight is something that people might be able to latch on to faster from a layman perspective. Examples of vectors: linear momentum, acceleration, displacement, right? Velocity, linear velocity, force, electric field, polarization. Then there's also angular velocity, and then there's angular momentum. Now, some of these things may not be familiar to you, and that is fine. Don't worry about it. Just hang on, listen, right? You will catch what we're saying as we go along. So, what is the difference between a scalar and a vector? A scalar quantity is a quantity that has magnitude alone. All right, so we're discussing now properties of these quantities, right? So magnitude is what we're talking about when we're talking scalar. Let me hold this book here because I might need to refer to the example, all right? A vector quantity, on the other hand, as soon as you say something is a vector, by direct implication, there is some kind of directional property to the whole thing, all right? So magnitude is one thing, direction is another thing. So for example, if I say that somebody walked a distance of 5 kilometers, that's a scalar, that's distance. All right? Saying that a person walked a distance of 5 kilometers, that is all the information I have. However, if I say that a person walked a distance 5 kilometers due east, now we're getting more specific. Because instead of just having a distance anywhere, we now have a very specific direction, which is in the direction of east. All right, so generally speaking, we get more information from a vector than we get from a scalar. All right, if we say somebody, let me see. If we say somebody climbed a distance of 2 meters, it doesn't say whether the person climbed up or whether the person climbed down, right? Again, we're talking about distance alone. That is scalar. If we say the person climbed up or the person climbed down, at that point, we now imposing a specific directional quality to the climbing. It's no longer just, okay, the person climbed, but how does the person climb? In what direction does the person climb? All right, and that is essentially the difference between a vector and a scalar. All right. The other thing I want to introduce, and which is something that I haven't seen too many people talk about, is the whole idea of a position. All right? Because implicit in the whole context of direction is a sense of position. And when we talk about position, we're talking about specifically with reference to some reference point then, in relation to some reference point. So when we say that a person walks 5 kilometers east, it means that we're starting from somewhere to go east. When we say that the person climbs 2 meters up from where? Where is your reference point to be talking 2 meters up? Now, even if the person didn't start moving from the reference point, and I'll go into that a little later, the fact that we're referring to up means that there is some place, some point that defines what up is and what down is. The fact that we're talking about east or west or north or south means that there is some place, some location, some point that by its very location is the definition of what east is, of what west is, of what north is, of what south is. All right? So, for example, if we're talking about up and down, the reference point is generally speaking, for purposes of overall geography, your references is sea level. So we talk about 2 meters above sea level, 2 meters below sea level. All right? If you're operating within a more specific context, you might be drawing something in a room or something, and you might actually define what the reference point is. That is fine. But I want to use the overall context of general geography so that hopefully you get the idea a little clearer, because geography is something that we understand intuitively because we all, generally speaking, are accustomed to moving, whether it's within our village or within our home or from one town to the next or from one country to the next. We understand instinctively the whole idea of movement. All right? And once we're talking movement, we're talking direction. And once we're talking direction, we're talking position. And that is, to me, one of the best analogies that I could use to explain the whole concept of scalars and vectors. So we're talking east, west, north, south. Right? East with reference to what? North with reference to what? Your cardinal points. We define something that defines the cardinal points. So again, for the purposes of overall geography, if we're talking east, we're talking about the Greenwich meridian, and I would have used this specific example in my discussions on coordinate geometry, which we'll come to within the context of vectors, because coordinate geometry is tied to vectors in the sense of assigning directions and positions and locations, but we will get to that a little later. All right? So if we're talking east and we're talking west, we're talking Greenwich meridian. There's this one line running north to south on the surface of the earth. Anything to the right of that is east, anything to the left of that is west. And if we're talking north and south, we're talking the equator. Anything above that is north, anything below that is south. So, to the general idea of direction, where the vectors are concerned, I also want to add position, because implicit in direction is also a sense of position. Position. Where is this thing located? And how does it move from one point to another point? You're talking position implicitly. All right? So, the scalars, the thing that the scalars have is quantity. How much of something? How far the person moved. That's a scalar. How high the person climbed. That's a scalar. All right? If we're talking vectors, we're talking direction. What direction the person moving? So we're now talking about a very specific movement. 5 kilometers east, as opposed to 5 kilometers west, as opposed to 5 kilometers south, as opposed to 5 kilometers north, or anything in between that. And then, well, with respect to climbing, it's either 2 meters up or 2 meters down. And then, of course, we're talking about position, right? 5 kilometers east. Okay, where did he start? Did he start in Port of Spain? Did he start in Arima? Did he start in San Fernando? Did he start in Claxton Bay? Did he start in Kingston, Bridgetown, Castries, St. George's, Rousseau, Georgetown, etc., etc.? Where did he start from to make this movement of 5 kilometers east? His position. Where did he start to climb from to make this movement of 2 meters up? Did he start from sea level? Maybe he started below sea level and he went up. We're talking direction, but we're still talking position because we're talking relative to some reference point, in which case the negative quantities will come in, but we will deal with that later. All right? Etc., etc., etc. So inherent in the vector quantity is direction, and position. Inherent is in the scalars is just quantity. So just to recap, most textbooks, most teachers, most websites on the internet, they will describe the difference between a scalar and a vector as being one of the scalar is quantity alone. The vector is quantity and direction, because you also have quantity with the vector too, but in addition to quantity, you also have direction. The directional aspect, the direction is what separates the vector from the scalar. In addition to that, however, I would also like to add position. All right, there is no inherent sense of position where the scalar is concerned, but as soon as you're talking direction, implicit within that is a sense of position. Where are you located? Where is this thing happening? Right? So scalar is quantity alone. The vector is direction and position. And that's basically it. All right? So that's it. We open the discussion. We open in salvo. All right? We discuss the topic. We talk around the topic. And then we start to get more and more into the mathematics of it. All right? So stay tuned. We have the next video coming up where we'll go a little deeper into this whole thing about vectors and scalars, etc., etc., etc.